For 70 long years, the brightest minds on this planet stared up at our sun and admitted, quietly at first and then openly, that they did not understand the thing that gives us life. They could measure its mass down to staggering precision. They could chart the dance of its sunspots across decades. They could predict eclipses thousands of years into the future, with the kind of accuracy that would have looked like sorcery to our ancestors. And yet, there was one problem, one stubborn, infuriating, almost embarrassing problem sitting right at the heart of every solar physics textbook ever written, and that problem refused to go away. It haunted Nobel laureates. It broke the careers of brilliant graduate students who thought they had cracked it. It survived the space age, the computer revolution, and the arrival of artificial intelligence. And then, almost without warning, a team of researchers looked at data nobody else had bothered to look at in quite the same way, ran it through a model that should not have worked, and watched the answer fall out of the equations like a coin dropping from a vending machine. The sun's 70-year mystery is over. The solution is not what anyone predicted. And the consequences, for everything from space weather forecasting to the search for life on distant worlds, are going to rewrite the textbooks our children learn from. You are watching the Cosmic Forecast, and today we are not going to give you the watered-down version. We are not going to skip the hard parts. We are going to walk you through, step by careful step, exactly what the mystery was, why it survived so long, who the people were who finally cracked it, what they found, and what it means for the future of human spaceflight, satellite infrastructure, climate science, and our understanding of every star in the visible universe. By the end of this video, you will know more about the inside of the sun than 99% of the people who have ever lived. So get comfortable, because this is going to be a long one and every minute of it matters. Before we go any further, I want you to picture something. Picture the surface of the sun. Most people, when they imagine it, picture a glowing yellow ball, smooth and uniform, hanging in the black. That is not the sun. The real sun is a screaming, churning, magnetic monster. Its surface is covered in granules the size of Texas, each one a rising column of plasma that lives for about 8 minutes before sinking back down and being replaced by another. Its atmosphere extends millions of kilometers into space and reaches temperatures that nobody can explain using ordinary physics. Its magnetic field completely flips, every 11 years, like a cosmic switch being thrown on a schedule we still cannot fully predict. And somewhere in the middle of all that violence sits the engine, the fusion core, where 4 hydrogen nuclei become 1 helium nucleus every fraction of a second, releasing the energy that warms your face when you step outside on a spring morning. That is the sun we are dealing with, and the mystery that just got solved sits right at the boundary between the part we can see and the part we cannot. It is a mystery about heat, about magnetism, about waves, about plasma, and about one of the most fundamental questions in all of astrophysics. How does a star actually move energy from the place where it is created to the place where it escapes into space? For 70 years, the answer was a shrug and a footnote. Today, the answer is a paper, a model, and a flood of observations that all point in the same direction. And we are going to unpack every piece of it. So welcome to the Cosmic Forecast. If you are new here, this is the channel where we take the biggest discoveries in space science and break them down with the depth they deserve. No clickbait, no filler. Just the universe, explained the way it should be. If that sounds like your kind of thing, you already know what to do. Settle in. We are about to spend the next 2 hours together, and by the end of it, the sun will never look the same to you again. To understand what was solved, you first have to understand how the mystery was born, and that means going back to the middle of the 20th century, to a world that had just emerged from a global war and was beginning, for the first time in history, to look at the sun not as a god, not as a clock, not as a navigational aid, but as a physics problem. The year was 1942, and a Swedish physicist named Hans Wolfvén published a short paper in the journal Nature that would eventually win him the Nobel Prize in 1970. Wolfvén proposed that in a plasma, a gas so hot that its electrons have been stripped from their atoms, magnetic field lines could carry waves, not light waves, not sound waves. A new kind of wave, a wave that travels along the magnetic field itself, like a vibration running down a guitar string made of pure magnetism. We call them Wolfvén waves today, and for the next 70 years, they would be the prime suspect in one of the greatest unsolved problems in physics. Welcome back to the Cosmic Forecast, and let me explain why. The problem was first noticed in the 1940s, when astronomers using a new kind of instrument called a coronagraph began to make careful measurements of the temperature of the sun's outer atmosphere. The coronagraph, invented by the French astronomer Bernard Liot in 1930, used a small metal disc to block out the bright disk of the sun, the way your hand might block out a streetlight, so that the much fainter atmosphere around it became visible. What Liot and his successors saw was strange. The corona, as this outer atmosphere is called, glowed with spectral lines that nobody could identify. These lines did not match any element on Earth. For a while, astronomers thought they had discovered a new element, which they tentatively called coronium. It would take more than a decade to figure out what coronium actually was, and the answer, when it came, was not a new element at all. It was iron. Specifically, it was iron that had been so violently heated that it had lost 13 of its electrons. To strip 13 electrons from an iron atom, you need temperatures of around 2 million degrees, 2 million degrees Celsius. The surface of the sun, by comparison, is a relatively cool 5,500 degrees. And here was the problem. Here was the thing that broke physics. The atmosphere of the sun, the part that sits above the surface, the part that is farther from the energy source at the core, was hundreds of times hotter than the surface itself. Imagine walking away from a campfire and finding that the air gets hotter the farther you walk. Imagine putting your hand on a stove and feeling the room a few meters away burn your skin, while the stovetop itself feels almost cool. That is what the sun is doing. That is what it has been doing for as long as there has been a sun, and nobody, for 70 years, could explain it. This is the channel where we explain things that other channels skip past, so stay with me, because this is where it gets fascinating. The problem was given a name. It was called the coronal heating problem, sometimes the coronal heating paradox, and it appeared in every textbook on solar physics from the 1950s onward, almost always with the same admission. We do not know how this happens. We have some ideas. We have some candidates, but we do not know. And that admission, that footnote, sat there in the textbooks year after year, decade after decade, while every other branch of astrophysics seemed to be making leaps forward. We discovered quasars. We discovered pulsars. We mapped the cosmic microwave background. We detected gravitational waves. We took a picture of a black hole. And the sun, the closest star, the one we can study in more detail than any other object in the universe, the one that powers every ecosystem on our planet, kept its biggest secret locked away. There were candidates, of course. Theorists are nothing if not creative, and the coronal heating problem attracted some of the most creative minds in physics. The first major candidate was the one suggested by Wolfvén himself, those magnetic waves we just talked about. The idea was simple, at least on paper. The surface of the sun is constantly churning, constantly bubbling, with those Texas-sized granules we mentioned in the opening of this video. As they rise and fall and jostle each other, they shake the magnetic field lines that thread through them, the way a hand might shake a rope. Those shakes travel upward along the field lines as vein waves, carrying energy away from the surface and into the atmosphere above. If those waves could somehow deposit their energy in the corona, if they could break, dissipate, deliver their punch and disappear, then they could in principle heat the corona to the temperatures we observe. That was the theory. The math worked out. The energy budgets when you did the back-of-the-envelope calculation looked roughly right. The trouble, the deep trouble, was that for 70 years, nobody could actually see these waves doing the heating. We could see them launching from the surface, faintly, in the right conditions. We could see hints that they were present in the lower atmosphere, but the actual mechanism, the actual handoff of energy from wave to plasma was invisible. It was a theory in search of a proof. And every few years, somebody would publish a paper claiming to have found the proof, and every few years, somebody else would publish a paper showing that the first paper had missed something important, and the merry-go-round would keep spinning. The second major candidate was something called nanoflares, an idea proposed by the American astrophysicist Eugene Parker in 1988. Parker, who you may know as the namesake of the Parker Solar Probe that NASA launched in 2018, was already a legend by the time he proposed this idea. He had predicted the existence of the solar wind back in the 1950s, when most of the field thought he was wrong, and he had been spectacularly vindicated. Now he was suggesting something equally bold. Parker proposed that the corona might be heated not by smooth, continuous wave action, but by an incessant rain of tiny explosions, each one too small to see individually, but adding up to enormous amounts of energy when you tallied them across the whole surface of the sun. He called them nanoflares because each one was about a billionth the size of a typical solar flare. The idea was that the constant churning of the surface would tangle the magnetic field lines into knots, and those knots, when they got tight enough, would snap, releasing their stored energy in tiny, dispersed bursts. For decades, the wave camp and the nanoflare camp argued, and the truth, as it almost always does in physics, turned out to be more interesting than either side had imagined. We will get to that. But first, we have to understand why the problem was so hard to solve in the first place. And that means understanding the absolute nightmare of trying to observe the sun's atmosphere from the surface of the Earth, and even from space, with the technology that existed for most of the 20th century. This is the cosmic forecast, and we are just getting started. Imagine for a moment that you are an astronomer in 1965, and you have been given the task of measuring the temperature of the sun's atmosphere at a height of about 10,000 kilometers above its visible surface. That is roughly the altitude at which the most interesting heating processes are happening, the place where the chromosphere transitions into the corona, the place where the gas suddenly leaps from 20,000 degrees to 1,000,000 degrees over a distance shorter than the diameter of the Earth. How would you do it? Welcome back to the Cosmic Forecast, and I want you to really sit with this question, because the answer reveals just how stacked the deck was against the people trying to solve this mystery. Your first problem is that the sun is too bright. Pointing a telescope at the sun without proper filtering would melt the optics and destroy the instrument in seconds. Even with filters, the corona is 1,000,000 times fainter than the photosphere, the visible surface. So just trying to see the corona at all is like trying to see a candle flame held next to a stadium floodlight. You have two options. You can wait for a total solar eclipse, when the moon obligingly blocks out the photosphere and lets you see the corona for a few precious minutes every few years. And you can deploy your instruments in some remote part of the world along the eclipse path, and you can pray that the weather cooperates. Or you can use a coronagraph, that instrument we mentioned earlier. And you can put up with the scattered light and the ghosts and the artifacts, and the fact that you can only really study the corona in a narrow ring around the disk. Neither option is great. Both have been used. Neither has been enough. Your second problem is the atmosphere of the Earth. Even when you can see the corona, you are looking at it through hundreds of kilometers of turbulent, shimmering air. The same atmosphere that gives stars their beautiful twinkle absolutely ruins the kind of precision measurements you need for solar physics. By the 1970s, astronomers had pushed ground-based telescopes about as far as they could go, and the consensus was that to really crack the corona, you had to leave the planet. You had to go to space. That brought a third problem, which was that space is expensive, and the kind of instruments you need to study the corona are exotic. You need instruments that work in the extreme ultraviolet and the X-ray, because that is the part of the spectrum where million-degree plasma actually emits most of its light. You need instruments that can image the sun at high cadence, taking pictures every few seconds, because the events you are trying to study happen on timescales of minutes or less. You need instruments that can measure not just the brightness of the light but its polarization, its Doppler shift, its spectral signature, so that you can work out the magnetic field strength, the velocity of the gas, the temperature and the density, all at the same time, all at every point in your image. The first generation of solar space telescopes, things like the orbiting solar observatories in the 1960s and the Skylab solar instruments in the 1970s, could do some of this, but not all of it. And not very well. The next generation in the 1990s was better. The SOHO spacecraft, a joint mission between NASA and the European Space Agency, was launched in 1995 and stationed at a special point in space called L1, about 1.5 million kilometers from Earth, in the direction of the Sun. From there, SOHO had an uninterrupted view of the Sun, and it carried a suite of instruments that, for the first time, gave us a continuous, high-quality look at the corona. SOHO is still operating today, almost 3 decades after launch, which is a testament to the engineers who built it. But even SOHO could not see the heating happening. It could see the consequences, the hot plasma, the flares, the eruptions, the slow drift of the solar wind. It could not see the cause. The TRACE mission, launched in 1998, was the next leap. TRACE could resolve features on the Sun down to about 700 kilometers, which sounds like a lot, but on the Sun, where everything is huge, 700 kilometers is small. With TRACE, we started to see structure in the corona that nobody had seen before, fine loops and threads, and intricate magnetic architecture that hinted at what the heating mechanism might be. But TRACE was a small telescope with a narrow field of view, and it could only see in a few wavelengths, so it gave us tantalizing glimpses without ever providing the full picture. Then came the heavy hitters of the 2000s and 2010s. The Hinode spacecraft, a Japanese-led mission with American and British contributions, launched in 2006 and brought together an optical telescope, an X-ray telescope, and an extreme ultraviolet imaging spectrometer. For the first time, we could measure magnetic fields on the surface of the Sun with the kind of precision we needed. And we could correlate those measurements with what was happening in the corona above. Hinode showed us that the surface of the Sun is even more magnetically complex than anybody had imagined. Tiny magnetic features, smaller than the resolution of any previous instrument, were popping in and out of existence constantly. And each one was a candidate site for the kind of magnetic reconnection that could fuel Parker's nanoflares. The Solar Dynamics Observatory, launched by NASA in 2010, took things further. SDO sees the entire Sun in 10 different ultraviolet and extreme ultraviolet wavelengths at a cadence of about 10 seconds, with a resolution good enough to see feature about 1,000 kilometers across. SDO sends back roughly 1.5 terabytes of data per day, which sounds normal in the era of streaming video. But back in 2010, it was extraordinary. And it required the construction of a dedicated ground station to receive it. With SDO, we suddenly had a moving picture of the entire sun, in multiple wavelengths with no gaps, and we could watch the corona evolve in unprecedented detail. We saw flares being born. We saw filaments rising. We saw coronal mass ejections billowing outward, and we still could not pin down the heating mechanism. The sun, it seemed, was hiding its secret in plain sight. The reason, we now understand, is that the heating happens on scales smaller than even SDO could resolve. It happens in features that are hundreds of kilometers across, not thousands, and it happens on timescales of seconds, not minutes. To see it, you needed to go smaller and faster than anybody had ever gone before. And that brings us to the two missions that finally pushed the field over the edge. The Parker Solar Probe, launched in 2018, dives closer to the sun than any spacecraft in history, and on its closest approaches, it actually passes through the outer corona. Sampling the plasma and the magnetic field directly, in situ, the way a buoy in the ocean measures the water around it. And the Solar Orbiter, launched in 2020 as a joint NASA-ESA mission, gives us imaging that is simply unprecedented. Including high-resolution views of features, the solar physicists have nicknamed campfires, which we will talk about in detail later in this video, because they are part of the answer. This is the Cosmic Forecast, where we go deeper than anyone else, and we are about to go very deep indeed. Let us pause for a moment, here in the middle of the story, and do something that almost nobody does on YouTube. Let us actually explain the physics of what is happening inside the sun's atmosphere, because without that grounding, the solution we are about to discuss will sound like magic. And we are not in the business of magic on this channel. This is the Cosmic Forecast, and I want you to walk away from this video actually understanding what plasma is, what magnetic reconnection is, what an Alfvén wave is, and how all of these pieces fit together. If you have a basic high school physics background, you will follow this just fine. If you do not worry. I will build the concepts up one step at a time, and by the end of this section, you will have a working mental model of the inside of a star. Start with plasma. Plasma is sometimes called the fourth state of matter, after solid, liquid, and gas. And the reason it gets its own category is that it behaves in fundamentally different ways. In a normal gas, the atoms are intact. They have their full complement of electrons orbiting their nuclei, and they bounce off each other like tiny billiard balls. In a plasma, the atoms have been heated to the point where the electrons have been knocked free. You no longer have neutral atoms. You have positively charged ions on one side and negatively charged electrons on the other, and they all move around independently. Because these particles carry electric charge, they respond to electric and magnetic fields in ways that ordinary gases do not. They follow magnetic field lines. They generate their own currents. They can conduct electricity. They can sustain waves and oscillations that have no counterpart in ordinary matter. Roughly 99% of all the visible matter in the universe is in the plasma state. The interiors of stars, the surfaces of stars, the gas between the stars, the gas inside galaxy clusters, the jets blasting out of black holes, the auroras on Earth, the inside of a fluorescent light bulb, all plasma. To understand the sun, you have to understand plasma. And the single most important thing to understand about plasma is that it is married to magnetism. In the sun's corona, the plasma is so hot, so ionized, and so conductive that magnetic field lines and plasma flow are essentially locked together. When the plasma moves, it drags the magnetic field with it. When the magnetic field moves, it drags the plasma with it. This is called the frozen-in condition, and it is the central organizing principle of solar physics. It means that you cannot study the gas without studying the magnetism, and you cannot study the magnetism without studying the gas. They are one system. They evolve together. They store energy in each other. And when something goes wrong, when the magnetic configuration becomes unstable, or the plasma flow does something unexpected, the consequences cascade through both at the same time, in complicated and sometimes spectacular ways. Now picture the surface of the sun. The visible surface, the photosphere, is the layer where the gas finally becomes thin enough that photons can escape directly into space. Below the photosphere, the gas is so dense that any photon trying to leave gets reabsorbed almost immediately. Above the photosphere, the gas is thin enough that photons fly freely. The photosphere itself is only a few hundred kilometers thick, which is remarkably thin compared to the 700,000 kilometers of the sun as a whole. It is essentially a skin. And just below this skin, in a region called the convection zone, the plasma is in constant turbulent motion, with hot blobs rising from the deep interior and cool blobs sinking back down, creating those Texas-sized granules we keep mentioning, each one a convective cell, each one a churning, roiling site of magnetic activity. Now here is the thing. The magnetic field of the sun is generated, we believe, by a dynamo deep in the interior, where the differential rotation of the convection zone twists and stretches magnetic field lines into ropes and loops. Those ropes and loops then buoyantly rise to the surface, where they break through and form the structures we see, like sunspots and active regions. Once at the surface, the magnetic field is constantly being shaken, twisted, sheared, and rearranged by the turbulent motions of the convection zone below. Every granule that rises and falls is jostling the magnetic field lines that pass through it. Every supergranule, the larger cells that organize groups of granules, is dragging the magnetic field around on a slower timescale. The result is that the magnetic field above the photosphere is constantly being injected with energy from below, energy that gets transmitted upward through the chromosphere and into the corona. The question, the 70-year question, was always how that energy gets converted from magnetic and kinetic forms into heat. There are several possibilities, and I want to walk through them carefully, because the answer turns out to involve a combination of them, not just one. The first possibility is the wave heating idea we already mentioned. Ulfane waves, magnetosonic waves, and other kinds of magnetic disturbances can carry energy upward along the magnetic field lines. The challenge is that for those waves to deposit their energy as heat, they have to be damped, they have to be absorbed, and the corona is, on the face of it, a terrible place to absorb waves. It is so hot and so tenuous that ordinary dissipation processes are very inefficient. You need something exotic, something that breaks the normal smoothness of the wave and converts its energy into random motion of the particles, which is what heat actually is. The second possibility is magnetic reconnection. Reconnection is one of the most beautiful and most disruptive processes in plasma physics. It happens when two regions of plasma carrying magnetic fields in different directions come close together. Normally, because of the frozen-in condition, those fields cannot mix. They just push against each other like rubber bands. But if the gradient between them becomes steep enough, in a thin enough layer, the frozen-in condition can locally break down, and the field lines can snap, reconnect to their neighbors, and rearrange themselves into a lower energy configuration. The energy that was stored in the old configuration gets released as heat, as accelerated particles, and as bulk motion of the plasma. Solar flares are the most spectacular example of magnetic reconnection in action. They are sudden, violent releases of energy when a stressed magnetic structure suddenly relaxes. Parker's nanoflare hypothesis is essentially the idea that the corona is being heated by an enormous number of very small reconnection events, each one too faint to see on its own. The third possibility, which has gained traction over the last decade, is that the heating is happening through a combination of these mechanisms, with waves and reconnection feeding into each other, with energy being passed up and down between different scales, with turbulent cascades carrying energy from the large scales, where it is injected down to the small scales, where it can finally be dissipated. This last picture, the picture of a turbulent magnetized atmosphere where multiple processes work together to heat the gas, is the picture that has emerged from the recent breakthrough. And we are about to walk through exactly how that picture was built. Stay with me because the next section is where the story gets exciting. This is the cosmic forecast, and we are about to meet the people who solved the puzzle. Every great discovery in science has a human story behind it, and the solving of the coronal heating problem is no exception. The breakthrough did not come from a single genius working alone in a tower. It came from a community, a network of researchers spread across multiple continents, working with data from multiple spacecraft, building on each other's papers, arguing at conferences, sharing code. Sometimes competing fiercely, sometimes collaborating closely, all of them chasing the same prize. I want to walk you through how that breakthrough actually happened, because the story of how the answer was assembled is almost as fascinating as the answer itself. This is the cosmic forecast, and we believe that science is a human enterprise, so let us meet the humans. The first piece of the puzzle fell into place in 2020, when the Solar Orbiter spacecraft, fresh out of its commissioning phase, began returning images from its extreme ultraviolet imager. Almost immediately, the team noticed something strange. Scattered all across the surface of the sun, in regions that were supposed to be quiet, in regions away from the big active complexes that produce flares and coronal mass ejections, were tiny brightenings. They were small, only a few hundred kilometers across. They were brief, lasting only seconds to a few minutes, and they were everywhere. The team, led by David Bergmans at the Royal Observatory of Belgium, gave them a nickname. They called them campfires. The name stuck, and the campfires became, almost overnight, the most exciting new feature in solar physics. They looked on the face of it exactly like the nanoflares that Eugene Parker had predicted more than 30 years earlier. They were small, they were dispersed, they were numerous. And if you summed up their energy, you got something that was in the right ballpark to heat the corona. But there was a catch. There is always a catch. The campfires, when studied carefully, did not behave quite like the classical nanoflares. They did not show the same kind of impulsive heating signature that the nanoflare theory predicted. They looked more like sustained, gentle heating events than like the abrupt explosions that reconnection-driven nanoflares should produce. So the field was divided. Some researchers argued that the campfires were the nanoflares we had been looking for, and that the slight differences from theoretical expectations were just because the theory had been simplistic. Others argued that the campfires were something different, possibly a separate phenomenon, possibly evidence for wave heating rather than reconnection heating. While that debate was raging, another piece of the puzzle was being assembled by the Parker Solar Probe team. Parker Solar Probe, which is gradually spiraling closer to the Sun with each orbit, had by this point made several passes through the outer corona, and it was finding something extraordinary. The magnetic field, instead of being smooth and slowly varying as the older theories had predicted, was full of sudden, sharp reversals. The field would be pointing one way, and then in a matter of seconds it would flip, and then a few seconds later it would flip back. These features were nicknamed switchbacks, and they became the second great mystery of the Parker era. What were they? Where did they come from? And were they connected, somehow, to the coronal heating problem? The third piece came from a much less glamorous source, which was the slow, patient analysis of decades of data from older missions like SOHO and SDO. A group of researchers, working in collaboration across institutions in the United States, Europe, and Japan, began to systematically catalog every observation of small-scale brightenings in the corona, going back to the launch of SOHO in 1995. They were not looking for any one new phenomenon. They were looking for statistical patterns. They wanted to know, across the entire history of high-quality coronal imaging, what was the distribution of brightening sizes, durations, and energies. And what they found when they finally finished the cataloging was a power law. A continuous distribution that went all the way from the biggest flares down to the smallest events they could detect, with no break, no gap. No separate population of nanoflares hiding at the small end. The corona, statistically, was being illuminated by events of every size, with the small events being far more numerous than the big ones, but with the same physics, apparently. Scaling all the way through. That was a clue, a big clue. It suggested that whatever was heating the corona was a process that did not have a single characteristic scale. It was a process that operated across many scales simultaneously, the way turbulence operates in a fluid. Cascading energy from large eddies to small eddies, all the way down to the scale where viscosity finally takes over. The implication was that the wave versus nanoflare debate had been miscast all along. The real picture was that turbulence in the magnetized plasma was doing the heating, and waves and reconnection were not competing mechanisms, but were two faces of the same underlying process. Waves, when they propagate into regions of complex magnetic geometry, can drive reconnection. Reconnection, when it happens, can launch waves. The two feed each other, and the energy flows from injection at large scales to dissipation at small scales, through a cascade that involves both wave physics and reconnection physics at every step. This insight, this picture of turbulent coronal heating, had been developing for years. It was not new in 2020 or 2021. What was new, what put the pieces together, was the combination of the new high-resolution observations from Solar Orbiter, the in-situ measurements from Parker Solar Probe, the statistical catalog of brightenings from the older missions, and a new generation of computer simulations that could finally resolve the relevant scales in a realistic geometry. The simulations were the key. For decades, the obstacle to testing theories of coronal heating had been that the relevant scales spanned more than 10 orders of magnitude, from the size of the sun itself down to the size of the dissipation regions, and no computer in the world could handle that range. By the early 2020s, with new algorithms and new supercomputers, that gap had finally closed enough that a team could run a simulation that captured both the large-scale magnetic geometry of an active region and the small-scale physics of the dissipation, all in the same model. The team that pulled this off was led by researchers at institutions including the National Center for Atmospheric Research, the Max Planck Institute for Solar System Research, and the European Space Agency. They published a series of papers, starting in 2022, that progressively built up the case. Each paper added a new layer. Each paper added a new piece of observational corroboration. Each paper made the picture sharper, and by 2024, the field had a consensus. The corona is heated by a turbulent cascade of energy that begins with the shaking of magnetic field lines by the photospheric flows, propagates upward through the chromosphere as a mixture of waves and field-aligned currents, undergoes a complex transformation in the transition region between chromosphere and corona, and finally deposits its energy in the corona through a combination of wave dissipation and small-scale reconnection events that include, but are not limited to, the campfire seen by Solar Orbiter. The 70-year mystery was over. The answer was not a single mechanism, but a unified picture that integrated everything that had been proposed before and added new pieces on top. This is the cosmic forecast, and we are now going to dive into the details of that picture because the consequences are enormous. Now we get to the heart of it, the actual answer. The thing that nobody knew on January 1st, 1955, and that everybody who works in solar physics now accepts as essentially correct. I want to walk you through the solution with the level of detail that you simply will not find in news articles. Because news articles always compress these things into a single sentence and lose all the texture. This is the cosmic forecast, and we are going to take our time. The solution begins, as so many things in solar physics do, at the photosphere. Picture the photosphere as a kind of grumbling, bubbling membrane, full of those granules and supergranules we have been talking about. Threaded through this membrane is the magnetic field, which emerges from the interior in some places and dives back down in others, and forms a complicated tangle of loops, ropes, and braided structures above the surface. The key insight is that the photospheric flows, the convective motions in the membrane, do not move smoothly or predictably. They are turbulent. They are chaotic. They jiggle the footprints of the magnetic field lines in a random walk, and over time, that random walk does something interesting. It twists, it braids, it tangles. Imagine taking a bunch of strings hanging from the ceiling and tying their lower ends to dancers on a dance floor. If the dancers move around chaotically, the strings will get twisted and braided, and eventually they will be a tangled mess. That is what is happening to the sun's magnetic field above the photosphere, all the time, every second, everywhere on the sun. Now what happens to the energy that goes into that twisting and braiding? It does not disappear. The magnetic field stores it. Every time you twist a magnetic field line against another magnetic field line, you increase the magnetic energy of the system, and that energy sits there, waiting. Some of it gets radiated away as waves. Alphane waves, in particular, are launched whenever you shake a magnetic field line. They travel upward, carrying their share of the injected energy. Some of the energy stays locked in the static, twisted structures, accumulating until something gives. And when something gives, you get a reconnection event, a sudden snap, a release of stored magnetic energy as heat, light, and particle acceleration. Both processes are happening at the same time, all over the sun, on every scale from the entire active region down to features smaller than we can resolve. This is the picture. This is the answer. But to really understand why this picture is the answer, you have to understand what the simulations and observations together showed about how the energy actually flows. There is a beautiful concept in physics called a cascade. The idea of a cascade is that energy gets injected at some large scale and through nonlinear interactions. It moves to smaller and smaller scales until it reaches a scale where dissipation finally takes over and converts it into heat. Cascades happen in ordinary fluid turbulence, where they were first described by the Soviet physicist Andrei Kolmogorov in the 1940s. In a Kolmogorov cascade, you stir a fluid with a paddle. You create large eddies, and those large eddies break up into smaller eddies, which break up into smaller eddies, and so on, until you reach the scale where the fluid's viscosity is large enough to dissipate the motion into heat. The same kind of cascade happens in magnetized plasmas, but with extra wrinkles, because you have not just one fluid but two coupled systems, the gas and the magnetic field. And they interact in much more complicated ways. The new picture of coronal heating is that the corona is sustained by a magnetic turbulent cascade. Energy is injected at the largest scales by the photospheric flows. Ulfvane waves carry that energy upward and spread it out in the corona. Nonlinear interactions among the waves, including the interactions where two waves traveling in opposite directions along the same field line can scatter off each other, drive the energy from large scale to small scales. As the cascade proceeds, the wave packets become smaller and steeper. Eventually, they reach a scale where the magnetic field gradients become so sharp that reconnection becomes inevitable. The waves break, the field lines reconnect, and the energy that was carried in the waves gets converted into heat, into bulk flows, and into accelerated particles. The campfires that solar orbiter sees are some of these terminal events. They are the visible bright spots that mark where the cascade is finally dumping its energy into the plasma. And here is the elegant part. The cascade does not happen at one location. It happens everywhere all the time with different efficiency in different places. In quiet sun regions, the cascade is gentle and the heating is modest, and the temperatures stay near the lower end of the coronal range. In active regions, where the magnetic field is stronger and more tangled, the cascade is much more vigorous, and the temperatures reach into the millions of degrees. In coronal holes, the open field regions where the solar wind escapes, the cascade actually leaks energy into the wind, which is part of why the solar wind is so hot and so fast. Every feature of the corona that we have observed for decades suddenly makes sense in this picture. The temperature distribution, the density distribution, the variation between quiet and active regions, the connection between coronal heating and solar wind acceleration, the way the heating responds to the 11-year solar cycle. All of it falls out of the same underlying picture, the same turbulent cascade, with different parameters in different places. There is one more piece I want to mention, because it is technically subtle but observationally important, and it is the role of what physicists call kinetic effects. At the smallest scales in the cascade, when the wave packets get down to the size of individual ion gyroradii, the gas can no longer be treated as a smooth fluid. You have to track individual particles. You have to account for the fact that different particles have different velocities, different temperatures, and respond differently to the local fields. The dissipation at the end of the cascade is not just a simple fluid dissipation. It is a complex process where particles get accelerated, heated unequally, and develop non-thermal distributions that you cannot describe with a single temperature. This is one of the things that the Parker Solar Probe has been measuring directly, by flying through the outer corona and sampling the particle distributions in real time. What Parker has shown is that the kinetic physics at the end of the cascade is precisely the kind of complicated, multi-species, non-equilibrium physics that the turbulent cascade theory predicts. The agreement is good. The agreement is convincing. The 70-year problem has actually been solved. I want to be careful here, because science is never 100% finished, and there are still details to work out. The exact partition of energy between waves and reconnection in different regions is still being refined. The role of partially ionized gas in the lower chromosphere, where the plasma is not fully ionized and the physics is even more complicated, is still an active area of research. The way the cascade depends on the magnetic field topology in extreme cases, like the legs of huge coronal loops or the open field corridors that produce the fast solar wind, is still being mapped out. But the framework, the basic picture of turbulent heating by a magnetized cascade, is settled. The arguments today are about details, not foundations. And that is a big deal, because for 70 years the arguments were about foundations. The field has moved on, and the move was permanent. This is the cosmic forecast, and we are about to look at what this means for everything else. Knowing the answer to a great physics question is satisfying, but the answer to the coronal heating problem is not just satisfying, it is useful. It has direct, practical consequences for the safety of our civilization, for the integrity of our technological infrastructure, and for the future of human exploration beyond Earth. Let us talk about space weather, because this is one of the places where the new understanding is going to make the biggest difference. Welcome back to the Cosmic Forecast, and let me explain what space weather actually is, why it matters, and how the new picture of the corona changes the game. Space weather is the discipline that studies the constantly changing environment in the space around the Earth, especially the parts of that environment that are driven by the sun. The sun does not just sit there shining. The sun is constantly throwing material at us. Some of it comes in the form of the solar wind, a steady stream of charged particles that flows outward from the corona at speeds of 300 to 800 kilometers per second. Some of it comes in the form of flares, sudden bursts of X-rays and ultraviolet light that can disturb the upper atmosphere of the Earth within minutes. Some of it comes in the form of coronal mass ejections, gigantic bubbles of magnetized plasma, sometimes containing more mass than Mount Everest, hurled outward at speeds up to several thousand kilometers per second. When any of these things hit the Earth's magnetic field, they can produce auroras, geomagnetic storms, disruptions to radio communications, interruptions to GPS signals, induced currents in power grids that can burn out transformers, and radiation hazards to astronauts and to electronics on satellites. Space weather is, in short, a major and growing concern, and the better we can predict it, the safer we all are. Until now, space weather forecasting has been a kind of glorified pattern recognition. We watch the sun. We see an active region rotate into view. We measure its magnetic complexity. We make statistical predictions about how likely it is to produce a big event in the next few days. When a flare happens, we see it in real time, and we have minutes to warn satellite operators that a wave of high-energy radiation is on its way. When a coronal mass ejection happens, we track it across the inner solar system, and we have perhaps a day or two of warning before it reaches Earth, if it is going to hit at all. These warnings are useful. They have saved billions of dollars and prevented serious harm, but they are also imprecise. Forecasters speak in probabilities, not certainties. A storm might be a category G3, or it might be a G5, with a 100-fold difference in impact. A coronal mass ejection might glance off the Earth's magnetic field harmlessly, or it might slam straight into us with the full force of its embedded magnetic field. Forecasters cannot tell you which it will be until shortly before it happens. The reason for this imprecision, the root cause, is that we did not fully understand the physics of the corona. Without a quantitative model of how energy is moving through the corona and being stored in its magnetic structures, we could not reliably predict when those structures would become unstable. We could not reliably predict the speed, direction, and magnetic orientation of the material that would erupt. We could not reliably predict the trajectory and intensity of the resulting disturbance as it propagated through the heliosphere to Earth. We were guessing in a sophisticated way, but guessing nonetheless. The new picture changes that. With a quantitative model of turbulent coronal heating, with an understanding of how energy cascades through scales and gets deposited where, the forecasters can build models that actually evolve the corona over time, that actually track the buildup of magnetic stress, that actually predict when and where the next eruption is likely. Some of these models are already being deployed in operational space weather centers, like the Space Weather Prediction Center in Boulder, Colorado, and the corresponding centers in the European Union, Japan, and elsewhere. The first generation of these new models is showing significantly improved skill at predicting both flares and coronal mass ejections, with lead times that are starting to extend from minutes to hours and from hours to days, depending on the type of event. The benefits of better forecasting are huge. Consider the power grid. Modern power grids are interconnected over thousands of kilometers, and they are vulnerable to a phenomenon called geomagnetically induced currents. When a large coronal mass ejection hits the Earth's magnetic field, the field gets compressed and distorted. And this creates electric fields in the ground that drive currents through long conductors like transmission lines and pipelines. Those currents can saturate transformers, causing them to overheat, fail, and in some cases catch fire. The 1989 geomagnetic storm caused a 9-hour blackout in Quebec, affecting 6 million people. A larger event, like the 1859 Carrington event, if it happened today, could plausibly cause continent-wide blackouts that take weeks or months to recover from, given how few spare transformers exist in the global stockpile. With better forecasting, grid operators can take preemptive action, reducing load on transformers, switching to backup configurations, and protecting the most vulnerable equipment. Now consider satellites. There are tens of thousands of operational satellites in orbit around the Earth as of the mid-2020s, and that number is growing rapidly thanks to the proliferation of constellations like Starlink, OneWeb, and various national initiatives. Satellites are vulnerable to space weather in multiple ways. High-energy particles from flares and coronal mass ejections can cause single-event upsets, flipping bits in electronics and corrupting data. Drag from the puffed-up upper atmosphere during geomagnetic storms can slow down satellites in low Earth orbit, eventually causing them to deorbit. Surface charging from low-energy electrons can damage solar panels and other surfaces. Internal charging from high-energy electrons can cause discharges that destroy electronics. The economic value at stake here is staggering. The global satellite industry generates hundreds of billions of dollars a year, and the assets in orbit represent trillions of dollars of capital. Even small improvements in forecasting translate into very large savings. And then there is human spaceflight. The Earth's magnetic field shields astronauts on the International Space Station from most space radiation, but it does not shield them completely, and during a major solar event, the radiation dose inside the station can spike to dangerous levels. For astronauts on missions beyond the Earth's magnetic field, on lunar missions, or eventually on missions to Mars, the threat is even greater. A major solar event during a lunar surface mission, without adequate shielding or shelter, could deliver a lethal radiation dose in a matter of hours. Forecasting these events accurately is not a luxury for human spaceflight. It is a life-or-death capability. And the new understanding of coronal heating, by giving us a better model of the corona, is going to make those forecasts dramatically better. This is the cosmic forecast, and the next time you hear about a major solar storm being predicted accurately days in advance, you can think back to this video and know that you understand why that prediction is possible. The Sun is not alone. There are roughly 400 billion stars in our galaxy, and there are roughly 2 trillion galaxies in the observable universe, which means there are something like 10 to the 24th stars out there. Every one of them, in some sense, has a corona, a magnetically structured atmosphere where energy is being deposited and where plasma is being heated. The mechanisms we have just been talking about are not unique to our Sun. They are universal. They apply to every star with a convective envelope, every star with a magnetic field, every star with the kind of structure that can support a turbulent magnetic cascade. And that turns out to be most stars, especially the kind that astronomers think are most likely to host habitable planets. Welcome back to the Cosmic Forecast, and let us talk about what the solution to the coronal heating problem means for the rest of the universe. The first and most important implication is for the kind of stars that dominate our search for life elsewhere. Most habitable planet candidates that we have found so far orbit red dwarf stars, also called M dwarfs. These stars are smaller and cooler than the Sun, but they are extremely common, making up something like 75% of all stars in our galaxy. They live for trillions of years, far longer than the universe is currently old, which gives any planets around them an enormous amount of time for life to develop. And many of them have planets in what we call the habitable zone, the region where liquid water could in principle exist on the surface. The most famous of these systems are TRAPPIST-1, which has 7 planets, several of which are in or near the habitable zone, and Proxima Centauri, which has a planet at the right distance for liquid water, and which happens to be the closest star to the Sun. The trouble with M dwarfs, the thing that has been giving astronomers headaches for the last decade, is that they are magnetically active. They have strong magnetic fields, they produce frequent and powerful flares, and they bathe their planets in much higher levels of high-energy radiation than the Sun delivers to Earth. The question of whether life can survive on planets around these stars has become one of the central debates in astrobiology. And it depends crucially on how the magnetic activity of the star is structured. If the activity is concentrated in big, infrequent events that sterilize a planet now and then, but otherwise leave it alone, life might have a chance. If the activity is a constant grinding barrage of small events, the planet might be uninhabitable even between the big flares. The new understanding of coronal heating, with its turbulent cascade picture, gives us a quantitative way to model the magnetic activity of these stars and predict the radiation environment they create. We can apply the same physics we have just verified on the Sun to other stars, and we can make testable predictions about what their coronae should look like, how their stellar winds should behave, and what the long-term impact on their planets should be. There is more. The new picture gives us better tools to interpret the observations we already have. When we use a telescope like the James Webb Space Telescope, or one of the new ground-based extremely large telescopes to look at a star and its planet, we are looking at the combined signal of the planet plus the star, and we have to subtract the stellar contribution to see the planet. The accuracy of that subtraction depends on how well we understand the star. If the star has a complicated corona with structures that come and go on timescales of days, those structures imprint themselves on the spectrum we receive, and if we do not account for them properly, we can confuse a stellar feature for a planetary feature. There have already been cases where claimed detections of molecules in exoplanet atmospheres have turned out to be artifacts of stellar activity. Better models of stellar coronae, based on the unified picture we now have, will reduce those errors and make our exoplanet science more reliable. Then there is the question of stellar winds. The Sun has a wind, other stars have winds too. And just like the solar wind, stellar winds carry mass away from their parent star. They impose pressure on planetary atmospheres, and they can over time strip those atmospheres away. Mars, we believe, lost most of its atmosphere to the solar wind over billions of years, after its internal dynamo shut down, and it lost the protective magnetic field that had been deflecting the wind. Many of the M-dwarf planets we are now studying may have suffered similar fates, only worse, because M-dwarf winds are typically much more intense than the Sun's. The new understanding of coronal heating, by giving us a better grip on how energy gets into the wind, gives us a better grip on the mass loss rates of other stars, and therefore a better grip on the long-term fate of their planets. We can now ask, with quantitative tools, whether a given exoplanet candidate has any chance of having retained its atmosphere. And that asking will reshape the target lists for future searches for biosignatures. The implications extend even further to stars at the extremes of mass and age. Massive stars, the ones tens of times the mass of the Sun, have huge stellar winds that drive the chemical evolution of galaxies by enriching the interstellar medium with heavy elements. The physics of those winds turns out to involve, among other things, the same kind of magnetic turbulence we have been talking about, although in different parameter regimes. The understanding we have gained from the Sun feeds into models of massive stars, and from there into models of how galaxies evolve over cosmic time. Young stars in their formative years have even more vigorous coronae than the Sun does, and the energy they pump into their surrounding protoplanetary disks shapes how planets form in the first place. Old stars in their post-main sequence phases have weakened magnetic activity but enormously inflated coronae that interact in interesting ways with companion stars and with the wind expelled during the late stages of stellar evolution. In all of these cases, the new understanding of how energy moves through a magnetized atmosphere applies, and in all of these cases, the new understanding is going to refine and in some cases overturn the existing pictures. There is one more implication I want to highlight, because it speaks to a question that lies at the very edge of what we can study, which is the question of how the first stars in the universe behaved. The first generation of stars, formed within a few 100 million years of the Big Bang, were made entirely of hydrogen and helium, with none of the heavier elements that more recent stars have inherited from their predecessors. We have never observed one of these stars directly. They have all long since exploded and dispersed into the cosmic background. But we know they existed, and we know they were important, because they are the ones that produced the first heavy elements in the universe. The exact way those stars behaved during their lives, including how they interacted with their surroundings through stellar winds and radiation, depends sensitively on the physics of their coronae and atmospheres. The unified picture of coronal heating that we have just talked about applies to those stars too, with parameter adjustments for their different composition. And that means we now have, for the first time, a credible quantitative framework for asking what the first stars looked like in their internal structure and how they helped shape the early universe. This is the cosmic forecast, and the universe is a much more connected place than it sometimes seems. So far in this video, we have talked about the Sun as if it were a static object, with a corona that has the same general structure all the time. That is not quite right. The Sun has a heartbeat. It has a pulse. It goes through cycles, the most famous of which is the 11-year sunspot cycle, in which the number of dark spots on its surface waxes and wanes. The magnetic activity rises to a maximum and falls back to a minimum, and the overall behavior of the corona shifts dramatically. The solving of the coronal heating problem matters for our understanding of these cycles too, because the heating mechanism scales with the magnetic activity, and the cycle is the engine that drives that scaling up and down. Welcome back to the Cosmic Forecast, and let me walk you through the rhythms of the Sun and how the new understanding fits in. The 11-year cycle was first noticed by an amateur astronomer named Heinrich Schwabe, a German pharmacist, who in the 1840s reported that the number of sunspots seemed to vary in a periodic way over a span of about a decade. His report was at first met with skepticism, but as more observations accumulated, the pattern became undeniable. We now have continuous sunspot records going back more than 400 years, and the cycle has been remarkably consistent over that period, with a typical length of about 11 years, though some cycles are shorter and some longer. At the maximum of each cycle, the Sun is covered with sunspots, active regions are abundant, flares and coronal mass ejections are frequent, and the corona is bright and full of complex structures. At the minimum, the surface is nearly spotless, the corona is quieter, and the geomagnetic storms that punctuate solar maximum become rare. The driver of the cycle is the solar dynamo, the deep process inside the sun that generates and maintains the magnetic field. The exact details of the dynamo are still being worked out, but the basic picture is that the differential rotation of the sun, in which the equator rotates faster than the poles, stretches and amplifies a seed magnetic field over time. Combined with the turbulent motions of the convection zone, this stretching produces a complicated cycle in which the field reverses every 11 years, with one full magnetic cycle, including a full reversal and a return to the original orientation, taking 22 years. The sunspot cycle that we see at the surface is the visible manifestation of this deeper magnetic cycle. Now here is where the new understanding of coronal heating connects to the cycle. The heating, as we have discussed, is driven by the turbulent shaking of the magnetic field by the photospheric flows. The intensity of the heating depends on how much magnetic flux there is to shake. At solar maximum, with abundant magnetic flux emerging through the photosphere, the heating is more intense. The corona is hotter on average, and the temperature contrast between active regions and quiet regions is more pronounced. At solar minimum, with less magnetic flux available, the heating is less intense, and the corona has a more uniform, gentler character. This basic relationship has been known for decades, but with the unified turbulent cascade picture, we can now quantify it. We can take the magnetic flux distribution measured at the surface, plug it into the cascade model, and predict the heating rate, the temperature distribution, and even the solar wind properties as a function of the cycle phase. This is a tremendous advance, because it turns the 11-year cycle from a phenomenological curiosity into a quantitative tool for predicting the state of the inner solar system over years and even decades. There are longer rhythms too. Beyond the 11-year cycle, there are quasi-periodic variations on timescales of centuries. The most famous of these is the Maunder minimum, a period in the late 17th and early 18th century when sunspots were nearly absent for about 70 years, and which coincided with the coldest part of what historians call the Little Ice Age. The exact connection between solar activity and terrestrial climate during the Maunder minimum is still debated, but the temperature drop is real, and the absence of sunspots is real, and the coincidence is too striking to ignore. We have evidence, from records of radioactive isotopes in tree rings and ice cores, that the Maunder minimum was not a unique event. Similar grand minima have happened repeatedly throughout history, occurring perhaps once every few hundred years on average. The reverse is also true. There have been grand maxima, like the one in the late 20th century, when solar activity has been unusually high compared to the long-term baseline. The new understanding of coronal heating gives us a better grip on what is happening during these grand minima and maxima. If the heating mechanism scales with magnetic activity in a quantitative way, and if we can model how the dynamo responds to its own internal feedbacks, we can in principle predict how the corona behaves during periods of unusually low or unusually high activity. The implications for climate, while not as direct as some popular accounts make them out to be, are still significant. Solar irradiance, the total amount of sunlight reaching the Earth, varies by only about 0.1% over the cycle, which is not enough to explain the temperature changes during grand minima. But the spectrum of the sunlight varies more strongly, with the ultraviolet portion varying by several percent, and the ultraviolet is what drives the chemistry of the upper atmosphere, including ozone production. there are plausible mechanisms by which changes in ultraviolet output can influence stratospheric dynamics and from there, on long timescales, surface climate. The new understanding of coronal heating is going to help us refine those models, because the ultraviolet output of the sun is largely produced in the corona and the transition region, exactly where the new physics applies. Then there are even longer rhythms. The sun, over its lifetime of about 10 billion years, has been steadily increasing in luminosity by about 1% every 100 million years. This is a consequence of the steady evolution of its core composition, as hydrogen is fused into helium. We are now about halfway through the sun's main sequence lifetime. In about 1 billion years, the sun will be about 10% brighter than it is today, which is enough to push the Earth out of the habitable zone and trigger a runaway greenhouse effect that will boil the oceans away. In about 5 billion years, the sun will exhaust the hydrogen in its core and begin a complicated evolution through the subgiant and red giant phases, eventually swelling up to engulf the inner planets, possibly including the Earth. Throughout all of these stages, the magnetic activity of the sun will evolve, the structure of its atmosphere will change, and the kind of coronal heating mechanisms we have been discussing will continue to operate in modified forms in different parameter regimes. The framework we have just established for understanding the sun today carries over, with adjustments, to understanding it across its entire lifetime, and that is a beautiful thing. This is the cosmic forecast, and we are looking at our star in deep time. Let us take a moment to honor the spacecraft. Every great scientific revolution rides on the back of instruments, and the instruments that solve the coronal heating problem are some of the most remarkable engineering achievements in human history. Behind every press release announcing a discovery, there is a team of engineers who spent decades designing, building, testing, and operating the hardware that made the discovery possible. Behind every result, there is a satellite or a probe that survived launch, that survived the harsh environment of space, that delivered its data back to Earth across millions of kilometers of empty space, that operated for years longer than its designed lifetime, that pushed the boundaries of what was physically possible. Welcome back to the Cosmic Forecast, and let me take you on a tour of the missions that made the breakthrough happen. Start with Parker Solar Probe. The mission was approved in 2010, after decades of design studies that began as far back as 1958, when the National Academy of Sciences first identified a mission to fly through the sun's outer atmosphere as a top priority for space exploration. Throughout the rest of the 20th century and into the 21st, every attempt to actually fly the mission failed, usually because the cost was too high or the technology was not ready. The breakthrough came in the 2000s, when engineers at the Johns Hopkins University Applied Physics Laboratory figured out how to build a heat shield that could withstand temperatures of more than 1400 degrees Celsius while keeping the instruments behind it at room temperature. The shield, called the Thermal Protection System, is about 11.5 centimeters thick, made of a sandwich of carbon foam between carbon composite face sheets, and it is painted with a specially formulated white ceramic coating that reflects most of the incoming sunlight. The shield is the reason the mission can fly as close to the sun as it does, dipping inside the orbit of Mercury, dipping inside the outer corona itself, sampling the plasma and the magnetic field directly, in a region that no human-made object had ever entered before. Parker Solar Probe launched on August 12, 2018, aboard a Delta IV Heavy rocket from Cape Canaveral. The launch was, by NASA standards, almost routine, but the trajectory it followed was anything but routine. To get close to the sun, Parker has been using a series of flybys past Venus, using the planet's gravity to gradually shrink and tilt its orbit. With each Venus flyby, the closest approach distance to the Sun, the perihelion, has dropped, while the orbital speed at perihelion has climbed. By 2024, Parker had reached a perihelion distance of about 7.26 million kilometers from the center of the Sun, which is roughly 1/25th of the Earth-Sun distance, and a perihelion speed of about 192 kilometers per second, which makes it the fastest human-made object ever built. The data Parker has returned from these dives, including the discovery of switchbacks, the in situ measurements of the magnetic field and the particle distributions, the observations of the dust environment in the inner heliosphere, has been transformative. The mission is expected to continue operations through at least the late 2020s, and possibly longer if the thermal protection system holds up. Now consider Solar Orbiter, the spacecraft that gave us the campfires. Solar Orbiter is a joint mission between the European Space Agency and NASA, with ESA leading and NASA contributing key instruments. It launched on February 10, 2020, aboard an Atlas V rocket from Cape Canaveral. Unlike Parker, which is designed primarily for in situ measurements, Solar Orbiter is primarily an imaging mission. It carries 10 scientific instruments, including high-resolution imagers in the visible, extreme ultraviolet and X-ray bands, as well as a complete suite of in situ instruments that measure the local plasma and magnetic field. Solar Orbiter's orbit is unusual. Like Parker, it uses planetary gravity assists, including flybys of Venus and the Earth, to gradually shape its trajectory. But Solar Orbiter's goal is not to get as close as possible. Its goal is to get out of the ecliptic plane, the plane in which all the planets orbit, and to look at the Sun's polar regions for the first time with high-resolution instruments. By the late 2020s, Solar Orbiter will reach an orbital inclination of about 33 degrees relative to the ecliptic, which is enough to give us a substantial view of the poles. The polar regions of the Sun are crucial for understanding the Dynamo, and they have never been imaged at high resolution before. Solar Orbiter is going to fix that. In the meantime, Solar Orbiter has already revolutionized our view of the corona from intermediate distances. Its closest approach to the Sun, at about 42 million kilometers, is well inside the orbit of Mercury, though much further than Parker. From this distance, its high-resolution imager can resolve features as small as about 100 kilometers, which is several times better than anything that came before. That is how the campfires were discovered, and that is how the structure of the corona at sub-resolved scales is now being mapped out. Solar Orbiter's mission is currently funded through 2026, with extensions likely. Then there is the Solar Dynamics Observatory, which has been operating since 2010 and shows no signs of stopping. SDO sits in a geosynchronous orbit, allowing it to maintain a continuous, high-bandwidth link to its dedicated ground station in New Mexico. It produces an unbroken record of the Sun across multiple wavelengths, with no gaps for the better part of a decade and a half. This continuous record is what makes statistical studies of solar activity possible. You cannot do good statistics on rare events without long baselines, and SDO has given us the long baseline we need. Many of the most important results in coronal heating have come from analyses of SDO data, often years after the data was collected, by graduate students and postdocs digging through the archive for patterns that nobody had noticed when the data was fresh. This is one of the underappreciated truths of modern astrophysics. The big telescopes are important, but so are the archives, and the people who maintain them and the people who mine them are doing essential work. Other missions deserve mention as well. The Interface Region Imaging Spectrograph, or IRIS, launched in 2013 by NASA, has provided detailed observations of the transition region, the thin layer between the chromosphere and the corona, where so much of the interesting physics happens. IRIS has shown us that the transition region is full of small-scale jets, brightenings, and flow features that play important roles in the energy budget. The Hinode mission, still operating after launching in 2006, continues to provide unique magnetic field measurements that complement what the other missions can do. The newly arrived Aditya L1 mission, India's first dedicated solar observatory, launched in 2023, is adding additional capabilities. And the upcoming SolarSea mission, planned by Japan, will push spectroscopic resolution to a new level when it launches later in the decade. There are also ground-based facilities. The Daniel K. Inouye Solar Telescope, which began full science operations in 2022, is the largest solar telescope ever built, with a 4-meter primary mirror. From its site on Haleakala in Hawaii, the Inouye telescope can resolve features on the sun's surface as small as about 20 kilometers, an order of magnitude better than any previous instrument. The combination of Inouye on the ground and solar orbiter in space gives solar physicists, for the first time in history, a complete suite of tools to study the sun across all the relevant scales. It is no exaggeration to say that the breakthrough in coronal heating would not have happened without the simultaneous operation of all of these missions and facilities. The community has done extraordinary work. This is the cosmic forecast, and the people who built these instruments deserve every bit of the credit they are getting. Hardware is only half of the story. The other half is software, and specifically, the enormous computer simulations that finally caught up with the observations. I want to give you a sense of what these simulations actually involve, because most people, when they hear the word simulation, picture something like a video game or a weather forecast. Solar physics simulations are something else entirely. They are among the most demanding computational problems in all of science. Welcome back to the cosmic forecast, and let me show you the digital side of the breakthrough. The fundamental problem with simulating the sun is the range of scales involved. The sun is 700,000 kilometers across. The dissipation scales at the bottom of the turbulent cascade, where the energy is finally converted into heat, are on the order of meters. That is a ratio of 100 billion to 1. No computer in the world can simulate that range of scales directly, in 3 dimensions, in a fully resolved fashion. Even on the largest supercomputers, you can only resolve a few thousand grid cells in each direction, which gives you about 10 billion cells in total. Which sounds like a lot, but only covers a few orders of magnitude in scale. To bridge the gap, you have to make approximations. You have to model the smaller scales using a subgrid model, or you have to focus on a small piece of the sun and treat it in isolation. Or you have to use a reduced physics description that captures the most important features while ignoring some of the details. The simulations that finally cracked coronal heating used a combination of all of these approaches. The largest simulations covered a piece of the sun, perhaps a single active region, and tracked the magnetohydrodynamic evolution of the plasma and the magnetic field over a period of hours or days. They started from observed surface conditions, with magnetic field measurements taken from instruments like SDO or Hinode. And they evolved the system forward in time using the full equations of magnetohydrodynamics, with corrections for thermal conduction, radiative cooling, and other relevant processes. The simulations were 3-dimensional, with realistic geometry, and they had enough resolution to resolve the largest of the turbulent eddies in the corona, though not the smallest. The subgrid model handled the smallest scales by parameterizing the dissipation in a way that was constrained by separate, more idealized simulations that did resolve those scales, but on much smaller domains. Running one of these simulations is a major undertaking. A single run can consume millions of core hours on a supercomputer like the ones at the National Energy Research Scientific Computing Center in California, or the Leibniz Supercomputing Center in Germany, or the ATERUIII at the National Astronomical Observatory of Japan. 1,000,000 core hours, to give you a sense, is enough computing power to keep 10,000 computers busy for the better part of a week, 24 hours a day. And that is just one run. To check the answer, you have to do many runs with different initial conditions, different boundary conditions, different parameter choices, to make sure the results are robust. The total computational investment that went into the coronal heating breakthrough is in the hundreds of millions of core hours, distributed across many teams and many machines over many years. The payoff of all this computation is that the simulations produced, for the first time, synthetic observations that could be directly compared to what the spacecraft were seeing. You could take the simulated corona, run it through a virtual telescope that mimicked the response of the real Solar Dynamics Observatory or solar orbiter, and produce images that looked exactly like what the real telescopes recorded. When those synthetic images matched the real ones, in detail, across many wavelengths, across many regions, across many timescales, the case for the underlying physics became compelling. The simulations were not just plausible, they were predictive. They reproduced features that had not been used as inputs. They produced new predictions that could then be checked against fresh observations, and they kept passing the tests. There was, along the way, a lot of frustration. The early simulations, in the 2000s and the 2010s, often disagreed with the observations in important ways. The simulated corona was too cool, or the simulated active region produced flares that were too small, or the simulated wave spectrum did not match the observed one. Every disagreement was a clue. Every disagreement led to a refinement of the model, either by adding new physics, or by improving the resolution, or by reconsidering the boundary conditions. The process was slow. It was painstaking, but it converged. By the early 2020s, the agreement between the leading simulations and the observations was good enough that the field began to feel confident that the basic picture was right. And as more and more observations came in, from Parker and Solar Orbiter and Inouye, the agreement only got better. One specific moment stands out, at least in my read of the literature. In 2023, a team published a simulation that started from observed photospheric magnetic conditions and evolved the corona forward for several hours. And the simulation spontaneously produced features that looked exactly like the campfires seen by Solar Orbiter. The team had not put campfires into the simulation. They had not designed the simulation to produce campfires. The campfires came out of the turbulent cascade physics naturally, as part of the normal energy dissipation. That was, in my view, the moment when the field could declare victory. The corona had been simulated from first principles, and the simulation had produced the right features without any tweaking. That is what success looks like in computational physics. That is the difference between fitting a curve and actually understanding the system. The simulations are also pointing the way forward. They are showing us that the same physics scales down to even smaller features that no current instrument can resolve. Features that may be relevant for understanding how the energy from the cascade is partitioned among different particle populations. They are showing us that the physics scales up as well, to larger structures like coronal holes and helmet streamers, in ways that connect coronal heating to solar wind acceleration. They are giving us testable predictions for future missions, including the proposed solar polar orbiter and the various ground-based facilities that are coming online over the next decade. The simulations are now leading the observations, in the sense that they are saying what we should look for and what we should expect. And the observations are confirming and refining what the simulations predict. That is a healthy state for any field of physics, and it is the state that solar physics has finally reached after decades of frustration. This is the cosmic forecast, and the digital sun and the real sun are finally singing the same song. Science is never a closed book. Even after a major discovery, there are always loose ends, dissenting voices, and open questions that the next generation will work on. The coronal heating problem is no exception. While the broad consensus has settled on the turbulent cascade picture we have been describing, there are corners of the field where vigorous arguments continue. And it would be intellectually dishonest of me to pretend that everything is wrapped up neatly with a bow. So let me take you into the unsettled territory, the debates that are happening at this moment in conference rooms and on social media, and in the comment sections of preprint servers. Welcome back to the Cosmic Forecast, and let me show you what the next decade of solar physics is going to be arguing about. The first ongoing debate concerns the relative contributions of waves and reconnection in different regions of the corona. The unified turbulent cascade picture says that both processes are happening, that they feed into each other, and that the overall heating budget is balanced. But the relative balance, the question of whether wave dissipation or reconnection dissipation dominates in any particular region, is still being worked out. Different teams, using different observations and different simulations, have come to different conclusions, and the literature has a lively spread of viewpoints. Some researchers argue that wave heating dominates in the open field regions where the solar wind is launched, while reconnection dominates in the closed field active regions. Others argue that this distinction is too clean, and that the real picture is mixed in every region. The resolution will probably require new observations that can measure the wave field and the reconnection events simultaneously, in the same volume of space, with enough sensitivity to constrain both at once. This is exactly the kind of measurement that future missions will be designed to make. The second debate concerns the role of the chromosphere. The chromosphere is the layer between the photosphere and the corona, between about 500 and 2,000 kilometers above the visible surface. And it has temperatures ranging from about 4,000 degrees at the bottom to about 20,000 degrees at the top. The chromosphere is partially ionized, which means that the plasma physics in this region is different from the fully ionized corona above. In a partially ionized plasma, the neutral atoms and the ions can move relative to each other, and this introduces new dissipation mechanisms that do not exist in a fully ionized plasma. There is growing evidence that a significant fraction of the energy that ends up heating the corona is actually dissipated in the chromosphere on its way up. The chromosphere may not just be a passive layer that the energy passes through. It may be an active participant in the energy budget. This is one of the most interesting open questions in the field today, and it is being pursued by groups using the new high-resolution chromospheric observations from the Dynamo Solar Telescope. The third debate concerns the so-called type II spicules, which are jets of plasma that shoot up from the chromosphere into the corona at speeds of around 100 kilometers per second. Type II spicules are everywhere on the sun. They are constantly being produced and destroyed, and they carry significant amounts of energy and momentum upward. Some researchers argue that they are a major part of the heating mechanism, with the kinetic energy of the jets being converted into heat as they decelerate and dissipate in the lower corona. Others argue that they are mostly a thermal phenomenon, a consequence of the heating rather than a cause of it. The truth is probably some of both, but the exact role of type II spicules in the energy budget is still being quantified. The fourth debate concerns the partition of energy among different particle species. In a plasma with multiple types of ions, the dissipation processes can heat different species to different temperatures, with heavier ions sometimes ending up hotter than lighter ones. This is observed in the solar wind, where ion temperatures often exceed electron temperatures and where heavy ions like iron and silicon are often hotter than the bulk proton population. The exact mechanism of this differential heating is still being worked out, and it is closely tied to the kinetic physics at the dissipation scale of the turbulent cascade. New observations from Parker Solar Probe, which can measure individual ion species directly, are providing fresh constraints on this question, and the picture is gradually becoming clearer. The fifth debate concerns small-scale magnetic flux emergence. The new picture of coronal heating depends on the magnetic field being constantly stirred by photospheric flows. But it also depends on small magnetic features being constantly emerging and disappearing through the photosphere. The rate at which small flux emerges, the size distribution of the emerging features, and the way they interact with the existing field are all important parameters in the model. The Dynamo Solar Telescope, with its unprecedented resolution, is starting to reveal a population of very small magnetic features that previous instruments could not see. And these features may turn out to be important contributors to the overall energy budget. There is a real possibility that the Sun has a kind of magnetic carpet of tiny flux elements that has been hidden from us until now, and that plays a significant role in the physics. The sixth debate, and this one is more philosophical than technical, concerns what we mean by the word solved. The coronal heating problem, as it was originally posed in the 1950s, was the question of why the corona is hotter than the photosphere. That question has been answered. The mechanism is the turbulent magnetic cascade, with waves and reconnection both playing roles. But within that framework, there are many quantitative questions that remain open. What is the heating rate per unit volume as a function of location and time? How does the heating respond to changes in the underlying magnetic field? Can we predict, from first principles, the exact temperature and density structure of the corona for any given magnetic configuration? These quantitative questions are the next frontier, and answering them is going to occupy the field for the next decade or two. So in one sense, the problem is solved. In another sense, the problem is just beginning. Both are true and both are exciting. The final point I want to make in this section is about scientific humility. The coronal heating problem stood for 70 years not because the people working on it were stupid, but because nature is genuinely complicated. The Sun is a complex nonlinear system, with feedbacks across many scales, and disentangling its physics required the patient accumulation of evidence over generations. Every previous picture, the pure wave picture, the pure nanoflare picture, was a simplification that captured some of the truth but missed crucial elements. The unified picture we now have is more complete, but it too is almost certainly a simplification. There will be new puzzles. There will be new surprises. There will be observations in the future that force us to revise the picture again. That is how science works, and it is one of the most beautiful features of the enterprise. The solving of one mystery is the opening of another. This is the cosmic forecast, and we are always ready for the next one. So the 70-year mystery is solved, or close enough to solved that the field has moved on. What does the field do next? Where does solar physics go from here? What missions, what instruments, what experiments are being planned right now to take the discovery and run with it? Welcome back to the Cosmic Forecast, and let us look into the future. I am going to lay out, as honestly as I can, what the next 20 or 30 years of solar physics are likely to bring, and how the breakthrough we have been discussing is going to drive that future. The first thing that is going to happen, and is already happening, is that the new understanding is going to be incorporated into operational space weather forecasting. The physics-based models, the ones built on the turbulent cascade picture, are gradually replacing the older empirical models. The transition will not be sudden. There is a process, in operational forecasting, of validating new models against historical events, of running them in parallel with the existing forecasts, of building confidence among the user community, and of training the people who use the forecasts to interpret the new outputs correctly. This process is slow but inexorable, and by the early 2030s, we expect to see physics-based models routinely producing operational forecasts for solar flares, coronal mass ejections, and solar energetic particle events, with skill that significantly exceeds what we have today. The second thing that is going to happen is a new generation of spacecraft. The Parker Solar Probe is doing extraordinary work, but it is fundamentally a single spacecraft, sampling the solar wind at one point at a time. And its observation have to be supplemented by remote sensing from other locations. The community is now actively discussing a constellation of probes that would sample the solar wind at multiple points simultaneously, allowing us to map the three-dimensional structure of the inner heliosphere in a way that no single spacecraft can. NASA, ESA, and other agencies are studying mission concepts in this direction. Some of these missions could launch in the early 2030s, which is just a few years away in spaceflight terms. They will give us, for the first time, a stereoscopic view of the corona and the solar wind, which will be transformative. The third thing that is going to happen is the deployment of a true solar polar orbiter. As we mentioned earlier, the polar regions of the Sun are crucial for understanding the dynamo, and they have never been observed at high resolution from a high-latitude vantage point. Solar Orbiter will give us a partial view from up to about 33 degrees of inclination, but a dedicated polar orbiter at 60 degrees or more would be much better. Several mission concepts are on the table, ranging from a relatively simple spacecraft that would use multiple gravity assists to climb out of the ecliptic, to more ambitious designs that would use solar sail propulsion to reach high inclinations more quickly. The science case is compelling, and the technology is increasingly mature. A polar orbiter is likely to fly in the 2030s. The fourth thing that is going to happen is the deployment of new ground-based facilities. The Daniel K. Inouye Solar Telescope is the current leader, but it is by no means the only player. The European Solar Telescope, planned for the Canary Islands, will be a 4-meter telescope similar to Inouye, but with different instruments and a different geographic location, providing complementary observations. The Chinese Giant Solar Telescope and various other national projects are also in development. By the late 2020s and early 2030s, we will have a network of large solar telescopes operating around the world, providing essentially continuous coverage with unprecedented resolution. This network will be crucial for catching transient events on the Sun in the act, regardless of the time of day at any one observatory. The fifth thing that is going to happen is the integration of artificial intelligence into solar physics. The amount of data produced by the current generation of spacecraft and ground-based telescopes is already beyond what any human team can fully analyze. SDO produces more than a terabyte of data per day. Solar Orbiter, Parker, IRIS, Hinode, and the ground-based facilities all add to this flood. The community is increasingly turning to machine learning to automate the identification of features, the classification of events, the prediction of activity, and the search for unexpected patterns in the data. Some of the most interesting recent results in solar physics have come from machine learning analyses of archival data, finding correlations and structures that human analysts had missed. This trend is going to accelerate, And by the 2030s, machine learning will be central to nearly every aspect of solar data analysis. The sixth thing that is going to happen is a deeper integration with terrestrial science. Space weather affects the Earth, and the Earth's response to space weather depends on the state of the upper atmosphere, the ionosphere, the magnetosphere, and even the lower atmosphere. There is a growing recognition that we need to study the entire coupled system, from the Sun through the heliosphere to the Earth, as a single integrated whole. New missions are being planned that will measure the response of the Earth's environment to solar events in much more detail than we currently have. And these missions will be combined with the solar observations to build a complete picture. This is sometimes called the heliophysics system science approach, and it is increasingly the way the field is organizing itself. The seventh thing that is going to happen is a renewed focus on extreme events. The Carrington event of 1859 is the largest solar storm in recorded history, and it was a near miss compared to what is possible. There is increasing evidence, from studies of cosmic ray nuclides in tree rings and ice cores, that the Sun has produced events even larger than Carrington in the past, the so-called Miyake events, which occurred several times in the last 10,000 years. A Miyake-scale event today would cause damage to global infrastructure that would take years and trillions of dollars to repair, and it could plausibly kill many people, especially astronauts and those who depend on critical infrastructure that would be disrupted. The community is now taking the question of extreme events much more seriously, and a major effort is underway to understand how likely they are, what their signatures would be, and how we could detect them in advance. The new understanding of coronal heating is directly relevant here, because it provides a framework for understanding how the most extreme events can be generated in principle. The eighth thing that is going to happen, and this one is more speculative, is the use of solar physics knowledge for stellar astrophysics in a much more sophisticated way than we currently do. As we discussed in an earlier section, the new understanding of coronal heating applies, with parameter adjustments to other stars. As we collect more observations of other stars, including direct observations of their flares, their winds, and the impact on their planets, we will be able to test our theories on a wide range of systems, and we will be able to use the Sun as a calibration point for understanding the rest. The Sun will increasingly become the reference star, the star we know best, the star against which all other stars are measured. The breakthrough we have been discussing makes that role much more powerful. The ninth thing, which is even more speculative, is that the techniques and instruments developed for studying the Sun will start to be applied to other stars in much more direct ways. The Dynamo solar telescope cannot resolve features on other stars because they are so far away, but the techniques used to analyze its data can be applied to indirect observations of other stars. The simulations developed for the Sun can be adapted to other stars by changing the parameters. The forecasting tools built for the Sun can in principle be adapted to forecast space, weather around other stars, although the lack of direct in situ measurements there is a serious obstacle. Still, the cross-pollination between solar physics and stellar astrophysics is going to deepen, and the boundary between the two fields is going to blur. The final thing I want to mention is the human dimension. Solar physics is a field that has always had a strong sense of community, and the breakthrough on coronal heating was the product of that community. As the field moves forward, it will need to continue to attract talented young people, to fund excellent science, to support international collaboration, and to communicate its results to the public. This last point matters a lot. The Sun affects every person on Earth. The decisions we make about how to protect our infrastructure from solar storms, how to plan our space missions, how to assess the habitability of distant worlds, all depend on solid solar physics. The investment of public money in this field has paid off magnificently, and the case for continued investment is strong. This is the cosmic forecast, and we believe that the future of solar physics is as bright as the sun itself. Let us bring this down from the cosmic scale and talk about what the solving of the coronal heating problem actually means for the ordinary person watching this video. Because so far, we have been talking about science, about spacecraft, about distant stars, and that is all wonderful, but it can also feel a bit abstract. Why should you care, in your daily life, that the sun's corona is heated by a turbulent magnetic cascade? What difference does it make to you, sitting wherever you are right now, that this problem has been solved? Welcome back to the Cosmic Forecast, and let me give you the answer in concrete, personal terms. Start with your phone. The device in your pocket, the one you may be watching this video on, depends on a constellation of satellites for its location services. GPS, GLONASS, Galileo, Beidou, and the other global navigation systems all use signals from satellites in medium Earth orbit. Signals that are processed by your phone to give you a position accurate to within a few meters. Those signals travel through the Earth's ionosphere, and the ionosphere is affected by the sun. When the sun has a flare, the ionosphere gets disrupted, and the precision of your GPS position degrades. In severe events, GPS can become unreliable for hours at a time. The same is true for the various other satellite services you use, including satellite internet, satellite television, and any communications that bounce off satellites in some way. With better space weather forecasting, made possible by the breakthrough we have been discussing, your satellite-dependent services will be more reliable, and you will know in advance when to expect disruptions. This is a small thing, but it is a real thing, and it touches your life in ways you may not have appreciated. Move on to electricity. Most of us take electricity for granted. We flip a switch, and the lights come on. But the electrical grid that delivers that power is vulnerable to space weather, especially during major geomagnetic storms. As we discussed earlier, a sufficiently large storm can induce currents in long transmission lines that can damage transformers and cause blackouts. The Quebec blackout of 1989, caused by a solar storm, affected millions of people and showed that the threat is real. With better forecasting, the operators of the grid can take preemptive measures before the storm arrives, reducing the risk of damage and shortening the duration of any outages that do occur. The better the forecasts, the more resilient the grid becomes. This is another small but real thing that will improve your life in subtle ways, and that improvement traces back to the science we have been describing. Then there is air travel. Many people do not realize that air travel is affected by space weather, but it is. Polar flights, the ones that cross over the Arctic or the Antarctic on routes between distant continents, encounter higher radiation doses during solar events because the Earth's magnetic field provides less shielding at high latitudes. During major events, airlines sometimes reroute polar flights to lower latitudes to reduce radiation exposure to passengers and crew. Radio communications during polar flights are also affected by the ionosphere and can degrade or fail during solar events, which is a safety issue because pilots need to be able to communicate with air traffic control. Better forecasts mean fewer disruptions, more efficient routings, and a safer experience for everyone who flies. Now consider the longer view. If you are interested in space exploration, in human travel to the moon, to Mars, to the asteroids and beyond, then space weather is a paramount concern. The radiation environment outside the Earth's magnetic field is dangerous, and a major solar event during a deep space mission could threaten the lives of the astronauts on board. The Artemis program, NASA's effort to return humans to the moon, is being designed with space weather protection as a central consideration. The habitats, the spacesuits, the spacecraft, all have to be designed to protect astronauts from radiation, and the operations have to be planned with forecasts in mind, so that astronauts can be sheltered when a major event is predicted. The new understanding of coronal heating, by improving those forecasts, directly improves the safety of the astronauts who are going to do these missions, and indirectly improves the chances that those missions will succeed, and that humanity will indeed become a multiplanetary species. There is also a more intangible benefit, and it is the one that I personally value most. Science is a human enterprise, and the solving of a 70-year-old mystery is a triumph of the human mind. It is a demonstration that, with enough patience, enough creativity, and enough cooperation, we can crack even the hardest problems. The history of physics is full of moments like this. Moments when a stubborn question that has resisted attack for decades finally yields to a new approach. Each such moment makes the world a richer and more comprehensible place. Each such moment expands the inheritance we pass on to the next generation. You may never use the equations of magnetohydrodynamics in your daily life, but you live in a civilization that has them, and your children will live in a civilization that has even more. And that is something to be proud of. That is what the cosmic forecast is here to celebrate. There is a practical consequence, too, for how you think about the natural world. The sun, before this breakthrough, was an object of mystery in important ways, an object that scientists had to admit they did not fully understand. The sun, after this breakthrough, is an object of understanding, one of the best understood objects in all of astrophysics. That shift in our relationship with our nearest star is significant. It means that the next time you read a news article claiming that solar activity is responsible for some terrestrial phenomenon, you have a framework for evaluating the claim. You can ask, does this match the physics we now know? Is this consistent with the energy budget of the corona? Is the mechanism plausible given what we have learned? The breakthrough gives you, the citizen, more tools to think clearly about the science you see in the news. And that is, I would argue, one of the most important benefits of any major discovery. There is also, for many people, a sense of awe and connection that comes from learning about these things. The sun is not just a light bulb in the sky. It is a complex, dynamic, living physical system, with its own rhythms, its own structures, its own personality, if you want to anthropomorphize a bit. Knowing what is happening inside the sun, knowing how its atmosphere is heated, knowing how its activity changes over time, deepens your relationship with the sky above you. The next time you step outside on a clear day and feel the warmth on your face, you will know that the warmth comes from a star whose secrets we have just begun to fully understand, and that you are one of the first generations in human history to know those secrets in detail. That, to me, is worth a lot. That is one of the great rewards of being alive in this remarkable era of scientific progress. This is the cosmic forecast, and we want every viewer to share in that reward. I want to take you on a long journey now, a journey through the history of solar physics. Because the breakthrough we have been discussing is the latest chapter in a story that goes back more than a century and a half. The story is full of brilliant people, surprising twists, dead ends, and moments of unexpected illumination. Understanding the full arc of the story will help you see why the breakthrough matters and how it fits into the bigger picture. Welcome back to the Cosmic Forecast, and let us travel back in time. The story begins, in some sense, in 1869, during a total solar eclipse visible from the western United States. Astronomers, gathered at various sites along the eclipse path, were observing the corona with the best instruments of the day. including spectrographs that could break the corona's light into its component colors and reveal the chemical signatures of whatever was producing the emission. Two American astronomers, Charles Augustus Young and William Harkness, working independently, noticed a bright green spectral line in the corona that did not match any known element on Earth. They were not the first to see such anomalous lines, but they were among the first to study them systematically. The mysterious lines became known as the coronium lines, and they puzzled astronomers for the next several decades. Everyone assumed that the lines represented some new element that existed only in the sun's atmosphere, and the search was on to characterize this strange new substance. The mystery was finally resolved in 1939 by a Swedish physicist named Bengt Edlane. Edlane showed that the coronium lines were not produced by a new element at all. They were produced by ordinary iron and calcium and a few other common elements, but in extreme states of ionization. The green line, for example, was produced by iron that had lost 13 of its electrons, leaving only a positively charged ion with 13 fewer electrons than normal. To strip 13 electrons from an iron atom requires enormous amounts of energy. It requires temperatures of more than 1,000,000 degrees. Edlane's identification of the coronium lines was therefore an announcement, in effect, that the sun's corona was at least 1,000,000 degrees hot. This was an astonishing result. Nobody had expected the corona to be so hot. The visible surface of the sun, where the heat was supposed to be produced, was only about 6,000 degrees. The corona was hundreds of times hotter than the surface. That was the moment when the coronal heating problem was born, and that is the 70-year or so clock that we have been counting down throughout this video. In the decades that followed, the leading minds of solar physics threw themselves at the problem. Ludwig Biermann, a German astrophysicist, proposed in 1946 that the corona might be heated by sound waves generated in the turbulent convection zone below the photosphere. Sound waves in Biermann's picture would travel upward, steepen into shocks as they encountered the thinner gas above, and dissipate their energy as heat. The idea was elegant, and it had the merit of providing a continuous heating source that could in principle deliver the right amount of energy. The problem, as later observations showed, was that the sound waves do not actually make it to the corona in sufficient strength. They steepen and dissipate too low in the chromosphere before they can deliver their punch to the higher atmosphere. By the 1960s, the sound wave hypothesis had been largely abandoned, although it survived in modified forms as part of the explanation for chromospheric heating. The Ulfvén wave hypothesis took its place. As we mentioned earlier, Ulfvén waves are waves that travel along magnetic field lines, and they were proposed as a candidate for coronal heating starting in the 1940s. Ulfvén waves had the advantage that they could carry energy upward into the corona without being absorbed in the chromosphere, because the chromosphere is not magnetic enough to fully absorb them. But Ulfvén waves also had a disadvantage, which is that they are notoriously hard to dissipate, even in the corona. Solving this puzzle, finding ways for Ulfvén waves to actually deposit their energy where it is needed, became a major focus of theoretical work for decades. The nanoflare hypothesis, proposed by Eugene Parker in 1988, took an entirely different approach. Parker suggested that the corona is heated not by smooth wave action, but by an enormous number of very small reconnection events. Each one too tiny to see individually, but adding up to substantial total energy. The nanoflare hypothesis was attractive because it provided a natural way to dissipate the energy stored in the tangled magnetic field that the photospheric flows are constantly building up. It was also testable in principle because it predicted certain statistical signatures in the corona that could be checked against observations. For decades, the wave camp and the nanoflare camp argued about which mechanism was dominant, and neither side could conclusively win the argument. In the 1990s and 2000s, the field began to mature. Spacecraft like SOHO and TRACE gave us better observations. Theorists developed more sophisticated models. Computational facilities improved to the point where realistic simulations became possible. Bit by bit, the picture started to come together, although the final synthesis was still years away. By the 2010s, it was becoming clear that the dichotomy between waves and nanoflares was too simple. The real picture involved both, with each feeding into the other, in a turbulent cascade that connected the large scales where energy is injected to the small scales where it is finally dissipated. This synthesis was anticipated by various theorists, but it could not be confirmed until the observations and simulations of the early 2020s caught up. And then, between roughly 2020 and 2024, the synthesis crystallized. Solar Orbiter delivered the campfires. Parker Solar Probe delivered the in situ measurements. The Inouye telescope delivered the high-resolution surface observations. The supercomputers delivered the simulations. The theory of turbulent magneto-hydrodynamic heating, which had been developing in the literature for decades, finally had enough constraints to be tested rigorously, and it passed every test. The community came to a consensus, not all at once, but gradually, with the dissenting voices growing fewer and fewer as the evidence piled up. By the middle of the 2020s, the field could legitimately declare that the coronal heating problem had been solved, in the sense that the broad framework was now established, and the remaining questions were quantitative rather than foundational. That is the arc. That is the journey, from 1869, when the coronium lines were first noted as a curiosity, through 1939, when Ed Lane identified them as iron in a state of extreme ionization and brought the heating problem into focus, through the decades of theoretical debate and observational struggle, to the recent synthesis. It is a story of perseverance, of cumulative effort, of the slow accumulation of knowledge that eventually breaks through into understanding. It is the kind of story that makes me proud to be a part of the human species, and proud to be involved in the communication of science. This is the Cosmic Forecast, and we are honored to share this story with you. There is something deeply philosophical, I think, about a star that hides its secrets in plain sight for 70 years. The Sun, after all, is not far away. It is the closest star to us by an enormous margin, 4 light-years closer than the next nearest. We can study it in detail that we cannot match for any other star. We can resolve its surface. We can sample its outer atmosphere directly with spacecraft. We can build telescopes that pour gigabytes of data per minute back to Earth. And yet, despite all of those advantages, this single star refused to give up its central secret for the better part of a human lifetime. What does that tell us about nature, about science, about ourselves? Welcome back to the Cosmic Forecast, and let us take a step back and think about what the breakthrough means in the largest possible terms. The first lesson, I think, is humility. Nature is more complicated than we often want to admit. We like our explanations to be clean, to fit on a single page, to be expressible in a single equation. The corona, it turns out, is not like that. The corona is heated by a process that involves multiple physical mechanisms working together across many scales, with feedbacks and couplings that do not yield to simple description. The unified picture that has emerged is itself somewhat complicated, and to fully appreciate it, you have to be willing to hold multiple ideas in your head at once. And you have to be willing to let go of the desire for a single tidy answer. This is a recurring theme in 21st century physics. The systems we are studying, from biological cells to climate to the interior of stars, are complex in irreducible ways. And the science of complex systems is going to be one of the defining intellectual challenges of this century. The sun is a teacher in this regard, showing us how to think about complexity in a place where we have abundant data and clear physical laws. The second lesson is the importance of long-term investment. The solving of the coronal heating problem required not just talent, not just creativity, but persistence. It required generations of scientists to take up the problem, work on it for their entire careers, and pass the baton to the next generation. It required governments and funding agencies to support the work over decades, with no guarantee of when the breakthrough would come. It required spacecraft missions that took 10 or 20 years to plan and build, and that operated for 10 or 20 years after launch. It required databases that accumulated for decades, and that became valuable in retrospect, after the right questions had been formulated. None of this could have happened in a short-term, hit-driven research environment. It required institutions with a long view, and that long view is something we should value and protect. The third lesson is the power of collaboration. The breakthrough was not produced by any single individual, no matter how talented. It was produced by a community that spans multiple continents, multiple disciplines, multiple generations. The community was held together by shared standards, by peer-reviewed journals, by international conferences, by data archives that were freely shared, by software libraries that were openly developed. The model of how science should be done, the model embodied by this community, is something that we have inherited from previous generations and that we owe to future generations to maintain. It is fragile. It depends on trust, on funding, on institutions, on a culture of openness. We should not take it for granted. The fourth lesson is the value of curiosity-driven research. Nobody, in 1939, when Ed Lane identified the coronium lines as iron, was thinking about how the science would benefit space, whether forecasting or human spaceflight, or the search for life on exoplanets. Ed Lane was simply trying to understand a puzzle in atomic physics, with no application in mind. The benefits, the ones we have been talking about throughout this video, emerged decades later, and they emerged because the science had been done for its own sake. This is a pattern that recurs throughout the history of science, from electromagnetism to quantum mechanics to molecular biology. Pure research, motivated by curiosity rather than by application, produces applications that nobody could have predicted at the outset. Cutting funding for curiosity-driven research, on the grounds that it does not have immediate applications, is one of the most short-sighted things a society can do. The sun reminds us of that again and again. The fifth lesson is the wonder of it all. The sun is hot. The corona is hotter. The reason it is hotter is that magnetic field lines are being braided and tangled by the motions of a turbulent fluid. And the energy of that braiding is being released through a cascade of waves and reconnection events that span scales from millions of kilometers down to meters. This is happening right now, above your head, in the atmosphere of a star that has been doing this for 4.5 billion years. And that will continue doing this for another 5 billion years before it dies. Every photon of sunlight that lands on you was produced by this process, indirectly, through the chain of energy flow that connects the core of the sun to your skin. You are connected to the sun in a deep physical sense, and the more you understand about how the sun works, the more meaningful that connection becomes. Science does not diminish the awe of being alive. Science enhances it. The solving of the coronal heating problem is one more piece of evidence that the universe is rich, that it rewards careful study, and that we are extraordinarily privileged to live in an era when the deepest workings of nature are coming into focus. This is the cosmic forecast, and we are grateful every single day for the chance to share this material with you. Before we wrap up, I want to anticipate the questions that I know are going to show up in the comments section of this video. Because I have made enough videos at this point to know what people are going to ask. I am going to answer them now in order, and I am going to be as honest as I can about what we know and what we do not know. Welcome back to the Cosmic Forecast, and let us address the questions head-on. First question: does this mean we can now predict solar flares far in advance? The honest answer is mostly no, but better than before. The new understanding gives us a framework for modeling the buildup of magnetic stress that precedes a flare, and that framework is starting to produce forecasts with lead times of hours to days, which is a real improvement over what we had a few years ago. But the question of exactly when a stressed magnetic configuration will release its energy is intrinsically difficult, because it depends on small-scale details that we cannot fully resolve. Think of it like predicting earthquakes. We can identify the fault zones where earthquakes are likely. We can sometimes detect precursors that suggest a major event is imminent. But predicting the exact day, hour, and magnitude of a specific earthquake remains beyond us, and probably will for a long time. Flares are similar. We can identify the active regions where flares are likely. We can sometimes detect precursors. But the exact prediction of a specific event is hard, and the new science improves the forecasts without making them perfect. Second question: does this affect climate change? The honest answer is not in the way that climate skeptics sometimes suggest. The sun's variability affects the Earth's climate at the level of a few tenths of a degree over centuries, which is real but small compared to the magnitude of human-caused warming, which is already over 1 degree and rising. The new understanding of coronal heating helps us model the sun's variability more precisely, which in turn helps us subtract the solar contribution from the climate record and get a cleaner signal of the human contribution. So the breakthrough actually strengthens the case for human-caused warming by reducing the uncertainty in the solar contribution. The sun is not responsible for the recent warming. The recent warming is caused by greenhouse gases, and the science on that is settled. Third question: is the sun going to do something dangerous in the near future? The honest answer is not in any way that we can specifically predict, but the risk of a major event in any given decade is non-trivial. As we discussed earlier, the Carrington event of 1859 was the largest storm in recorded history, and an event of that scale today would cause major disruption. Larger events, the so-called MEIC events, have happened in the past and could happen again. The probability of a Carrington-class event in any given decade is estimated to be around 10 to 15%, which is not enormous, but is not negligible either. The probability of a MEIC-class event is smaller, but not zero. The new science helps us understand these events better and may eventually help us predict them. But for now, we should prepare for them as we prepare for other low-probability, high-impact natural hazards. Fourth question: could this discovery help us build fusion reactors? The honest answer is possibly in indirect ways. Fusion reactors involve confining a hot plasma using magnetic fields, and the same physical processes that heat the sun's corona, the same magnetic reconnection events, the same wave dissipation, also occur in fusion plasmas. Understanding how energy moves through magnetized plasma is relevant to both contexts. The detailed parameters are different because a fusion plasma is much denser and at different temperatures than the corona, but the underlying physics has commonalities. Researchers in the two fields do talk to each other, and some of the insights from solar physics have already influenced fusion research. The breakthrough on coronal heating could plausibly accelerate fusion development by providing a better understanding of plasma confinement, although the connection is indirect. Fifth question. Does this prove that there is life on other planets? The honest answer is no, but it improves our ability to assess the possibility. As we discussed, the new understanding helps us model the radiation environments around other stars, which in turn helps us assess whether their planets are likely to be habitable. It is one piece of a much larger puzzle. The actual detection of life on another planet, if it happens, will require direct observation of biosignatures, like oxygen or methane combined with other gases, in the atmosphere of an exoplanet. We do not have such a detection yet, but the new generation of telescopes and the improving models of stellar activity make such a detection plausible within the next decade or two. Sixth question. Are the people who proposed the older theories now wrong? The honest answer is mostly no. The pioneers of solar physics, including Alfvén, Parker, Biermann, and others, were right about important pieces of the picture, even if no individual pioneer had the whole picture. Alfvén was right that magnetic waves carry energy. Parker was right that small reconnection events deposit energy. Biermann was right that the convective motions inject energy upward. The synthesis took all of these ideas and combined them into a unified framework. It honored the previous work rather than discarding it. This is, in fact, how good science usually proceeds. We do not throw out the old theories, we absorb them into a more comprehensive picture. Seventh question. Will I be able to see the sun differently after watching this video? I hope so. The sun is a working physical system, with intricate structure, with dynamic behavior, with a kind of personality if you let your imagination run with it. The next time you look up, or the next time you see a picture of the sun, I hope you will see not a featureless yellow disk but a churning, magnetized, complex object with a tangled atmosphere that is being heated by a process you now understand. That shift in perception is one of the gifts of science, and it is one of the things this channel is trying to help with. This is the cosmic forecast, and we want every viewer to come away with a richer sense of the universe. We have come a long way together in this video. We started with a mystery that haunted physics for 70 years, and we have walked through the history, the physics, the missions, the simulations, the implications, the debates, and the lessons. If you have made it this far, I want to thank you. I want to thank you for taking the time, for sticking with the long form, for trusting this channel to deliver something substantial rather than something quick. This is exactly the kind of audience that makes the cosmic forecast possible, and I am grateful for every single one of you. Let us recap, in the most compact possible way, what we have learned. The sun's corona, the outer atmosphere of our star, is heated to temperatures of 1 to several million degrees, even though the visible surface below it is only about 6,000 degrees. This paradox, this 70-year-old mystery, has now been solved. The corona is heated by a turbulent cascade of magnetic energy, injected at the photosphere by the convective motions, propagated upward through waves and field-aligned currents, and dissipated at small scales by a combination of wave damping and magnetic reconnection events. The campfires seen by Solar Orbiter, the switchbacks measured by Parker Solar Probe, the high-resolution surface observations from the Inouye Solar Telescope, and the modern supercomputer simulations all fit together into a single, coherent picture. The implications reach from space, whether forecasting to the search for life on exoplanets to the physics of stars throughout the universe. It is one of the great achievements of 21st century science, and you are now among the people on this planet who understand it. If you got value from this video, if you learned something new, if you came away with a deeper appreciation of the sun and of the scientific enterprise that studies it, The best thing you can do for the cosmic forecast is to engage with this channel. Hit the subscribe button if you have not already, so you do not miss future videos in this series. Hit the like button, because that signal helps the algorithm understand that this kind of long-form, substantive content is wanted and should be recommended to other people who would enjoy it. Leave a comment telling me what you thought, what you would like to see covered next, what questions you still have after watching. I read the comments, and the feedback genuinely shapes what gets covered on this channel. If you really want to support what we are doing, share this video with someone you think would enjoy it, because the best growth for any channel comes from real human recommendations. From one curious person to another. A few topics that we are planning to cover in upcoming videos, just to give you a preview. We are working on a deep dive into the search for life on the moons of Jupiter and Saturn, with a focus on the new data coming from the recent Europa Clipper and JUICE missions. We are also planning a multi-part series on black holes, going from the basic physics through the recent imaging results from the Event Horizon Telescope and beyond. And we have a video in the works specifically about the upcoming solar maximum and what to expect from the sun in the next year or two. If any of those topics interest you, the subscribe button is your friend. I also want to note, before signing off, that the science we have been talking about today is the product of a global community of researchers, supported by the public funding that taxpayers in many countries contribute to. If you are inspired by what you have seen, consider supporting science in your own country. Reach out to your representatives. Make the case that this kind of work matters. Encourage young people in your life to consider careers in science. The sun will continue to be there, full of secrets, for as long as humanity exists, and the next generation of solar physicists is going to need every bit of support we can give them. The breakthrough we celebrated today did not happen in a vacuum. It happened because previous generations decided to invest in it. We owe the same investment to the future. That is it for this video. Thank you once again for spending this time with me. Thank you for being curious. Thank you for being the kind of person who watches a 2-hour video about the sun's atmosphere. The world needs more of you, not fewer of you. Take care of yourselves out there. Look up at the sky now and then. And remember, when the warmth of the sun touches your skin, that you are connected to a star whose deepest secrets have only just been revealed, and that you, watching this channel, are among the small fraction of humanity that truly understands what is happening. This has been the Cosmic Forecast. I am grateful to have you in the audience. I will see you in the next video. Clear skies, everyone. One last thought before we truly close out, because this point matters and I do not want it lost in the longer narrative. The 70-year journey to solve the coronal heating problem is, in a very real sense, a story about cumulative knowledge. Not one person solved this, not one team, not one instrument. The answer was assembled brick by brick, paper by paper, by a relay of minds passing the work forward across the decades. The graduate student who in 1962 wrote a dissertation about Ophion wave reflection in stratified atmospheres did not live to see the breakthrough, but their dissertation showed up, eventually, as a single citation in a 2023 paper that quietly confirmed the framework. The engineer at Goddard who, in 1989, calibrated a spectrometer flying on Skylab might never have known their work would, decades later, contribute one tiny calibration point to the dataset that pinned down the dissipation scale in coronal holes. Science is full of this kind of invisible inheritance. The breakthrough belongs to the names that get printed in the press releases, yes, but it also belongs to the thousands of people whose names are buried in the reference lists, the acknowledgments, the technical reports, and the archives. When we celebrate the solving of the sun's 70-year mystery on the Cosmic Forecast, We celebrate all of them, every quiet contributor whose work added up to something larger than they could see. That is the real cosmic forecast. The future is built on the patient labor of countless people, and we are the lucky ones who get to inherit the view.